All right, grade 11, as we were learning about work and energy, an important concept that we are finding is that solving motion problems with energy and work can sometimes be easier than applying Newton's laws. Okay, so all the type of energy that's involved in motion is usually called mechanical energy. And it sums up in elastic potential energy, gravitational potential energy, kinetic energy, rotational energy. This is all energy involved in motion. And what we're going to do in this little video here is we're going to explore some simple relationships between elastic potential energy, gravitational potential energy, and kinetic energy. Those are the main three to begin with. All right, and we're going to just talk a little bit about what happens to work when it's done on systems, what happens to work that is done by systems, and understanding how to do energy transformations when I know what the equation is for the total mechanical energy of a system is. Okay, so let's take a look. Remember, a lot of these problems involve cars or roller coasters going up and downhill where gravitational potential energy is converted to kinetic, back to gravitational. Okay, so let's take a look at those three types of energies that I want to work on in this video. So elastic potential energy that I showed you in a previous video has a formula that looks like this. Okay, where K is the K constant of the spring, X is the displacement of the spring from equilibrium. So how much I stretch or compress the spring, I can calculate how much work I did and how much energy would be stored in that spring. Okay, now for gravitational potential energy, that is going to be mgh, okay, because this is the force of gravity that's pulling the object down, and height would be the difference in height. Okay, if I go back up here, the difference in height that I have to do work against gravity. So all that energy that I'm doing work against gravity with is going to be stored as potential energy. Okay, now all those potential energy sources can be converted into other types of energy sources. So once that potential energy is initiated into a conversion, one type of energy that is always being converted into is kinetic energy, the energy of motion. And kinetic energy has a formula of 1/2 mv squared, okay, where v is the velocity of your object, m is the mass of your object. So if I know how much potential energy a system has and it's converted all into kinetic energy, I'd be able to calculate the velocity. Okay, so for example, if gravitational potential energy is converted into kinetic energy, then mgh, all of that gravitational potential energy is going to be equal to 1/2 mv squared. On the other hand, if all the elastic potential energy is converted to kinetic energy, then I can say this, that 1/2 kx squared is equal to 1/2 mv squared. And I'd be able to solve for the velocity of an object leaving a spring. Okay, so we're going to be taking a look at these relationships in some example problems right now. All right, now before we move on, take a look at this. There's some things that I can cancel out. Okay, so when gravitational potential energy is converted to kinetic, the masses can cancel out. We've seen that in a previous video. Okay, when elastic potential energy is converted to kinetic, this 1/2 term can cancel out. That's kind of cool and can simplify things when we do our calculations. All right, so let's take a look at the first one. Now, we've been doing a lot of this, and you guys have been working through this in your simulation of a pinball machine. But I want to go through it again because it's just such a good model to build up. So in a spring launcher, when I pull back an object on the spring, I am loading that system. I am doing work on that system when I push that ball in. And the work that I do, that energy that I put in, is going to be stored in the system as elastic potential energy. And all of that energy is going to be conserved. Okay, if I don't have any friction on my surfaces, all of that elastic potential energy will be converted into kinetic energy, which will then be converted into gravitational potential energy up here. All right, so what's really important when you're doing these types of problems is to make a model of what's happening. So elastic potential energy in the system is going to be converted to kinetic energy, which is going to be converted into gravitational, I'm going to call it GEP, gravitational potential energy. Okay, and I can do some calculations along the way. Okay, or I can skip the kinetic energy and go directly up to here if I need to. All right, so let's take a look. So the first part of this problem says if the spring of the system is pulled back by 5 centimeters, calculate the velocity of the ball leaving the spring. Okay, so I did work. I put that spring back by 5 centimeters. And so that work that I did is going to be equal to elastic potential energy. And that elastic potential energy is going to be converted into kinetic. So I can say elastic potential energy is going to be equal to my kinetic energy after being launched, because all of that is conserved. Another way of saying the conservation of energy is my elastic potential energy minus the kinetic energy is going to be equal to 0, okay, because all the energy is conserved. All right, so when I put this like this, I can substitute the formulas. For elastic potential energy is kx squared. My kinetic energy is 1/2 mv squared. And now I can try to simplify the algebra before plugging numbers in. So that 1/2 goes away. And then kx squared over m square rooted is going to be equal to my velocity. Now notice I did a lot of algebra in my head. I don't like it. For you guys, I'd like you to do 2 or 3 steps. But the final should look something like this. Okay, so now that I have that, I can then substitute the numbers in. So 100 newtons per meter times 0.05 squared divided by the mass of that ball, which is 1 kilogram, square rooted would give me my velocity, which I'm not going to solve, but you can solve with your calculators. So that would tell me the velocity of a ball being launched. And that's really, really quick. Okay, in class the other day, some people were trying to calculate the force that spring would apply. And then from going from force and the distance coming back, trying to then work out what that kinetic energy would be, which is easy to do. You can do that, but it's a little bit of extra work. Okay, this puts it right there in 2 or 3 simple steps. So sometimes conservation of energy gives us solutions quicker than Newton's laws would. Okay, so let's go to the next problem, which is calculate the maximum vertical height. So the maximum vertical height would be this, which is doing work against gravity. So what we're looking at now is the conservation of energy. The kinetic energy of that ball will be converted into gravitational potential energy. So the vertical one, all right? So then I can say 1/2 mv squared, or my kinetic energy, is going to be equal to my gravitational potential energy, which is going to be equal to mgh. Now the interesting thing here is the m's will cancel out, all right? And if I want to calculate h, I have 1/2 v squared over g is going to be equal to h. Okay, and so that's the equation that I just developed. I've solved for v up here, so I can plug that in here, and I divide by g, and I'll be able to calculate h. Another thing I could do to calculate the h is not even calculate velocity at all. I can just calculate the elastic potential energy, which is going to be the same as my kinetic energy, and then go straight from there to calculate the gravitational potential energy. So instead of using kinetic energy, I could just use my elastic potential energy, and then went from there. Okay, and that should yield the same answer, okay, in a different way. Okay, so that's the benefit of using conservation of energy. Then, as a final question, to actually calculate the distance the ball rolls up the ramp, well, I'm not going to solve that, but to calculate the distance the ball rolls up the ramp, I just have to use trigonometry, because once I solved that side, and I have this angle, it's opposite hypotenuse, it's a sine function that would then tell me how far that ball is going to go up the ramp, okay? Assuming that there's no friction. If there's friction, the problem becomes a little bit more challenging, which we'll see one of the groups present in the pinball machine, okay? Instead of these 3 simple terms, I would then have to add work done against friction into my conservation of energy problem, okay? So that's pretty simple. All right, now here's a problem that is pretty classic. It's a lab that we would have likely done if we were in school. We would attach a ball onto a string, a 1 meter string, and hung it from the ceiling. And we would attach a razor blade onto the top of one of our tables. And we would allow this ball to swing down, okay? And it would then cut, the razor would then cut the string right above the ball at that 1 meter mark, okay? So in that system, the total energy to start with, now what kind of energy does that ball have? What did we load it with? Well, we had to do work against gravity to lift that ball up. Okay, so we had to lift this ball up by that change in height. Okay, if that ball was would be down here. We had to lift that ball by that change in height. Okay, so we had to do work against gravity. So this ball has gravitational potential energy. And then that gravitational potential energy is going to be converted into kinetic energy. Okay, right at that point. So all that gravitational potential energy that ball has up here is going to be converted into kinetic energy. And then that kinetic energy is going to have velocity. And then at this part of the problem here, we've seen this before. When we launch a ball horizontally off of a 1 meter table and it falls to the ground, okay, then we can use kinematics. So at the bottom part here, I can then use my kinematics equations for projectile motion to be able to solve this. So you'd likely have a problem like this on your semester exam for sure, because this combines kinematics with conservation of energy. It's super, okay? It's really, really nice, all right? I could also ask questions about the force of collision down here. So much stuff, all in one problem, okay? So let's use our knowledge of conservation of energy and kinematics to actually calculate this horizontal distance, okay? What would that horizontal range be of that ball after it left the table, okay? So in order to do that, we need a series of steps. First, I need to, like I showed you in the diagram above, okay, I need to convert gravitational potential energy into kinetic energy to find that exit velocity. What's the launch velocity? Once I have my launch velocity, I can then use my kinematics equations that we did for that particular problem, that horizontal launch. And then I'll be able to calculate everything you need, okay? So let's find part A. I'm gonna write here in green. So I'm gonna split this into part A. And part A is to calculate launch velocity, okay? And in that case, my gravitational potential energy is gonna be converted into kinetic energy. So then mgh, the work that I had to do against gravity to lift that object up, is going to be equal to 1/2 mv squared, where the m's cancel out. And to solve for v, we have 2gh square rooted is equal to v. Okay, that's what I want. But I've run into a situation. What is h? So if I go up here, h is this, but I don't have it. The problem didn't give me the h. The problem gave me 1 meter being the rope. Okay, so then this would also be 1 meter, that length over here. And then it gave me an angle. It gave me an angle. Well, I think I could use this, okay? So I have this side here, which is 1 meter, and that's the length of the rope, and this is a 30-degree angle. I would be able to calculate that, okay? So I'd be able to calculate that. And that would, 1 meter minus whatever that length is here, is going to give me the height that I actually lifted that up by. So how do I calculate this side? This is my adjacent. That's my hypotenuse, so it's a cosine function. Okay, so remember, cosine 30 degrees is equal to adjacent, which is what we're trying to solve, over 1 meter. Okay, so then cosine of 30 degrees times 1 meter is going to be that adjacent side, that x is what we called it. Okay, so that part up here is equal to cosine 30 degrees. That's kind of cool. Okay, like 0.886. All right, so then I can solve for that height by taking 1 meter minus x, which is minus cosine 30 degrees. So then I would say h is equal to 1 meter minus cosine of 30 degrees. Okay, so now that we come back over here, I can plug everything in. So the square root of 2 times 9.81 meters per second squared times 1 meter minus cosine of 30 degrees, okay, is going to give me my velocity. I'm not going to solve that. You can solve that on your calculators, okay? But once I have that velocity, I have the expression for it, I now have my horizontal velocity. So I got my horizontal velocity. Okay, and then the rest, I'm not going to solve for you. I'm just going to get you to go back to the kinematics videos. But remember, part 2 of this problem would be to calculate the time of flight due to gravity. Okay, so the time of flight is going to be limited by that 1 meter drop. Okay, so that object is going to drop 1 meter. The initial vertical velocity will be 0. So it's just like that classic problem. How long does it take for a rock to fall 1 meter? That'll be my time of flight. And then that time of flight multiplied by my horizontal velocity will give me my range. Okay, so then part 3 will be equal to time of flight multiplied by my horizontal velocity is going to equal to my range. Okay? All right, and then that's a great problem that reminds you of how to do projectile motion problems, and then using conservation of energy to quickly calculate the velocity of an object as it swung down here.